Alright, welcome everyone to Math 234. This is Chapter 12, the very first section, the three-dimensional coordinate system. In this video, we're going to try to do a couple things. Mainly, we want to upgrade from a two-dimensional system, x's and y's and stuff like that, to a three-dimensional system. We'd like x's, y's, and z's. So, what does that look like, right? So we want to be able to comprehend and visualize what is this three-dimensional system, and then our goal is to be able to plot a few points, at least, in space. So, let's get to it. There's lots of definitions here. Let me start with one, and I'm going to be jumping up and down and up and down. I'm going to be trying to draw these things as we go, more or less. So, okay. The first thing here is that we can define the coordinate axes. Coordinate axes. Looks like axes, but that's the plural for axis, is axes. All right, so this consists of course, the x-axis, our good old friend. Oops, let me go ahead and erase here. X-axis, the y-axis, and our new friend, the z-axis, which all meet at a common point and are perpendicular to one another. So let me go ahead and draw these up here. So usually the way that we draw these things, and I'm going to leave myself a little bit of room, you do the x is actually sticking out of the page. The y is kind of left and right now. Sorry, at a bit of an angle here. And then the z is up and down, right? So y used to be up and down. Now we have z is up and down. So this kind of describes space, right? It's not a two-dimensional system, it's a three-dimensional system. Notice they are all perpendicular to one another, right? So this is right here is a right angle. So y is perpendicular to z. X is perpendicular to y, but it's kind of at a weird angle. It's kind of maybe hard to see. And also x is perpendicular to z. So all of them are perpendicular to each other. That's the great thing about, right, space, a three-dimensional system, is that you can have multiple perpendicular lines, unlike in two dimensions. Of course, they all meet at this common point, right? So now going back down here to B, the common meeting point of the coordinate axes is again called the origin. So that's the same. So we can see here where they all meet, that point right there is called the origin. And then this is kind of complicated. But the claim is the picture that I drew up above was not random, right? So the direction of the z-axis is determined by what's called the right-hand rule. Right-hand rule. And I am personally left-handed, so I'm offended by this. But okay, whatever, right? So the idea here, I'm going to write it out. It's going to be kind of long and annoying, and then I'll go back up to the picture and we'll describe actually what's happening here, what I'm trying to write in words. So, okay, we're going to curl, oops, why is this angry with me? There we go. We're going to curl the fingers of your right hand around, getting ahead of myself here, around the z-axis, first, our fingers go through the x-axis, then the y-axis, and your thumb, let me rewrite that a little bit, your thumb points in the direction of the positive z-axis. So basically, this is a question of what is up and what is down, right? Because like I said, this is the most common picture. And the claim is if we curl our fingers, right? So our hands going around the z-axis, and we first hit the x, and then our fingers hit the Y, right, using our right hand here, our thumb should be pointing up. Okay, But if we were to draw a different sketch, for instance, if I was to draw X going this way and Y maybe sticking out of the page or something like this, then our fingers of our right hand would go through the X first, then the Y, and you would notice that if you're following along at home with your actual hand, right, holding it up to the screen, that your thumb is now pointing down. So actually the Z-axis points down. The right-hand rule is surprisingly important. That this will come up again here in 12.4, so we can't completely forget about this. But the main thing that I want you to take away from this is that it matters how you draw your picture. Again, these things aren't random, X sticking out, Y sticking out, Z sticking out. There's actually, kind of a formulaic way that we get these things, and it's called the right-hand rule. Okay, let's move on then. The three coordinate axes, right? Determine three coordinate planes. So the most, maybe our favorite, just because we know it a little bit better, is the XY plane. And the XY plane contains the X and Y axis, or Y axes, and so on, right? So the XZ plane would contain the X and Z axes. So let me go ahead and show you here. In this picture, my X-axis, my Y-axis, so the XY plane would be this one that's kind of level, right? So if I can go ahead and shade this in, this right here is the XY plane. It contains the X and the Y axis. It's kind of, a sheet of paper. Likewise, I'll try to draw my best. I'm sorry if it's not great, but the XZ plane. So the XZ plane would contain the X-axis and the Z-axis. It would stick out. It's kind of like an up and down piece of paper, but sticking out of the page. So here would be this green one right here, would be the XZ plane. And likewise, we have the YZ plane, and that's maybe even the best. This is just kind of the flat piece of paper. Again, it contains the Y-axis and the Z-axis. So it's these pieces of paper, essentially, these planes that are part of the space. Now, I don't blame you if you don't want to draw this all, right? It kind of looks messy. In fact, I'm going to erase this one. This picture looks a little bit better to me. But you can see, again, the purple one is the XY plane. And let me go ahead and label them. The green one here, this is going to be the XZ plane. And actually, this is a good time as any. I'd like to show you a nifty tool, right? So if you just go to Google here, this is what I did. It's called Monroe 3D Calc Plotter, right? So Monroe 3D Calc Plotter. This first one right here is an old one. It requires Java, right? Almost no browsers run Java anymore. So you need the Java code and all that sort of stuff. So this one's basically broken, but actually a couple more down, this is the new one that's coded with probably HTML5 and JavaScript and all that sort of stuff. And this is what it looks like, and I think this is a great way to be able to visualize, right? We have very static pictures, and you can only look at them from one direction, but the nice thing about this is that we can spin it around, right? And you can see kind of all the different angles, and you can see, maybe if I look at it from above, or let me kind of rotate this around so we can see in our standard picture, right? Ooh, hold on there. We have the X-axis over here, the Y-axis over here, and the Z-axis up top, right? And so if you follow the right-hand rule, it follows that, right? And you can do kind of all rotations of this, and you can see kind of nifty surfaces and whatnot. So this is one really cool surface, but they have all sorts of surfaces, right? So if I go over here, you can look at, oh, this is a crazy one, right? So this is the fun of Calc 3, right? That we're going to be doing three-dimensional stuff. So we have three-dimensional functions, all that sort of stuff. And it's not just surfaces that this thing graphs either. And we'll get more familiar with this later, but in particular for this section, right, we're going to be interested in points. So maybe you want the point, -1, 1, 1, right? And so I go ahead and graph that, and you can see, that's where the point is in space, right? So this is space. Okay, so this is a great visualization tool. I'm going to be using this a lot in class, I suspect. I just wanted to let you guys know about it. And of course, you can copy down the URL or stuff if you don't want to do a Google search. I would bookmark this. Like I said, I think we'll be back here quite often. So, okay. now that I got that out of the way, a nice little plug here, we can see all the planes and that stuff. I guess maybe I'll show you one of the planes. If I was to plot z equals 0, this looks like it contains the x-axis and the y-axis. So this is going to be the xy plane. Just like in 2 dimensions, the line y equals 0 is actually the x-axis, right? So the equation z equals 0 actually refers to the xy plane. Likewise, I'll do one more for you guys. Let's go ahead and do what's called an implicit surface here. Very simple one. I'm going to do the equation y equals 0. And you know, if we were betting, the equation y equals 0, just like z equals 0 down here was the xy plane, y equals 0, we're probably thinking that's going to be the xz plane. So let me go ahead and click. And there it is. And we can see, yes, it includes the x-axis and the z-axis. So that's going to be the xz plane has the equation y equals 0. So again, this is a really cool tool for visualization, and I guess, yeah, like I said, I'll be back here quite often, I suspect. Okay, now we can visualize the planes and all that sort of stuff. We can see that the coordinate planes, if we graphed all of them, it would actually split space into 8 regions. Oh no, I'm very particular. I need everything in blue. Sorry. 8 regions. These, like before, when the plane gets split into 4 regions called quadrants, right? So if I go ahead, maybe I'll draw over here maybe. This is the XY plane, our good old friend, right? We had 4 quadrants. This was quadrant 1, quadrant 2, quadrant 3, quadrant 4, back in the day when we just had 2 variables. So now the claim is the coordinate planes divide space into 8 regions. These are called, well, coordinates go up to octants because there's 8 of them. And actually, so let's go ahead back here and let's help visualize this really quick. So let me go ahead and graph maybe one more of these things, an implicit surface, and I'm going to do x equals 0. That's going to be the YZ coordinate plane. Oops. And so you can see this splits it to 4 regions on top, 4 regions on bottom, right? So altogether there are 8 regions. So these are the 8 octants. All right. And then finally, one of them gets a name. So we have the first octant is in the foreground, determined by the positive axes. So it turns out there isn't a nice conventional way to enumerate these octants, but everyone has agreed that the one determined by the positive axes is going to be called the first octant. So it's the one, again, in the foreground, especially in this picture right here. It's the one that kind of pops out at you. Let me go ahead and see if I can get the picture. Yep. So it's this one that's kind of closest to us here, with the positive x-axis, the positive y-axis, the positive z-axis. This piece right here is the first octant. And again, the other ones, there isn't a second octant, there isn't a third, there isn't a fourth, anything like this, but there is a first. We have agreed on that. Okay, so I think we're starting to be able to visualize these things. The other objective that I wanted to get through in this video is to be able to plot some points in space, to be able to do this on a piece of paper. I know that we have computers and stuff, they're great for the visualization, but we want to be able to do this ourselves on quizzes and exams, right? We don't get calculators in this course. So, okay. Just as before, right, points in a plane were determined by xy ordered pairs. We're going to have xyz ordered triples, right? So no longer ordered pairs, but ordered triples. So a point P, so if I have like 1, 2, 3 here, the first thing right here, the 1 is going to be the x coordinate, the 2 is going to be the y coordinate, and the 3 is going to be the z coordinate, right? So, okay, I want to do something similar to this. I have a slightly different point here for this example. I have 1, negative 2, 3. I would like to be able to graph this on these coordinate axes, right? So I've already given them to you, the x, the y, and the z, and I've given us little dash marks as well. Okay, so the x is 1, right? So I go out 1 here. That's the x equals 1. Y equals negative 2. So again, this is the positive y-axis, so I need to go in the other direction. I need to go backwards 2. right? And it's kind of weird in the 3 dimensions, right? So I need to go backwards to this point right here, and then I need to go up 3. So if I go up 3, well, along the z-axis, that's that height, but notice it's kind of sticking out a little bit, and I had to go backwards some. So if I go up 3, the claim is it should be darn near right here. So this is P, 1, -2, 3. So that is the point 1, -2, 3. And so yeah, it's 3 dimensions. Sometimes it's very useful. You can see I'm drawing kind of almost a 3-dimensional box here. And it's kind of this outermost vertice of this box, right? So 1 in the x direction, -2 in the y direction, up 3 in the z direction. Okay? So that is the point 1, -2, 3. Of course, in this class, we're going to be graphing all sorts of things. It's not just going to be points. It's going to be surfaces. It's going to be curves, all these things. But we got to, maybe crawl before we walk or walk before we run, all that sort of stuff. So we're just going to focus on graphing some points here. Okay, now, it may not be obvious at this point, but later in this class, we're going to become very interested in what's called projections. We're going to take a point and be able to project it places. So here in this example, I have the point 2, 4, 3 graphed. So it's 2 out in the x direction, 4 out in the y direction, and 3 up in the z direction. And I would like to graph the projections onto the xy plane, call it Q, the xz plane, we're going to call it R, and the yz plane, and call it S. And this is going to be kind of like a little mini definition almost within this example. So, okay. If I was to take this point P and I was to smash it in to the xy plane, right? So that's my first one, Q. I was project it into the xy plane. Well, I would project it straight down, and it would be this point right here. This would be the point Q. Now, it still has the x and the y coordinate information, right? So it still has 2 and 4, but now it doesn't have any z, right? The z is no longer 3. It's been pushed down into the xy plane, so it has the z coordinate 0. Okay, so that's one projection. Let's project again. In this case, we're going to project to the xz plane. We're going to call it R. So I'm going to project it into the xz plane. That's this one over here, right? Okay, so if I was to project P into the xz plane, the claim is, right, it wouldn't have any y, right? So it'd be, looks something like this. It would project down into the xz plane. It would still have go out 2x, go up 3z, right? But the y would be 0. So R is going to have the coordinates 2, 0, 3. So that's the R point right there. And then finally, if I was to project into the yz plane again is this one that's nice and flat. It contains, again, the y-axis and the z-axis right there. So if I was to project this into the yz plane, again, it's like the x is killed off, right? There is no more x. It's pushed back here. And this is going to be my s. So it doesn't go out at all, right? The x coordinate now is 0, but the y and the z coordinates are maintained. So these are relatively simple projections, and in fact, you can see I've started to draw a piece of the box that I did before, right? So these projections have something to do with, the other vertices in this box, which is very nice. So these are, again, relatively easy projections. We're going to be doing more complicated things when we come to 12.3, but this starts getting your mind thinking about projections. Okay, the final little definition that I want to cover in this video, and this will be the last thing, I promise, right? The Cartesian product. So when I talk about space, right, the three-dimensional thing, this is denoted a couple different ways. One denotion is reals cross reals cross reals. So these weird bold R things. And we're going to use the set notation to define this. These are the ordered triples, x, y's, and z's. So they're ordered triples. And then we have a nice vertical bar, which means such that, right? Such that x, y, and z are all real numbers. So they're all in the reals right here. So this is the Cartesian product. Again, this is the set of ordered triples of real numbers. Sometimes it's denoted as this nice bold R thing cubed. And this is how we can talk about space. Because we do need to talk about, whether we're in a two-dimensional plane or three-dimensional space. So usually this R3 means that we have 3 coordinate axes, the x, the y, and the z. This is often called, right, the 3-dimensional rectangular coordinate system. And as you saw in Calc 2, we now know something about there are other coordinate systems out there, like polar coordinate systems, for instance. So in this class, we're going to talk about kind of upgrades of polar. They're going to be called cylindrical and spherical. So this is kind of the nice situation right here, the 3-dimensional rectangular coordinate systems. And you can see there's lots of rectangles that we've sketched here, right? So it kind of makes sense that this is very rectangular. So yeah, there will be other coordinate systems that we're talking about, but in this class, for now, it's going to be just the rectangular coordinate system. All right, that is it. I am done. I will see you guys in class and in the next video when we'll talk about 12.2. That's going to be about vectors. So I'll see you guys shortly. Thanks for watching.